Okay, so looking at the second derivative, what does the second derivative show? It shows us concavity. So what's happening is the second derivative is the change of slope. So what does the second derivative being positive mean? It means that the first derivative, the slope, is becoming more positive or increasing. So if I look at that, I can start with a negative slope here, sloping down. It doesn't have to be negative, but I'm just going to start with negative slope. It's going to become more positive, more positive, more positive, or in this case, less negative, less negative, less negative, which is same as more positive. And we end up with this curve. It's curving up. So we say that it's concave up. The opposite happens if the second derivative is negative. Second derivative negative means that the derivative is decreasing, or the slope is decreasing or becoming more negative. So if I start with positive slope, this becomes more negative or less positive. Less positive, more negative, more negative, more negative. We get this curvature, which we call concave down. So a negative second derivative indicates a concave down point. And where the second derivative is equal to 0, this is a potential change of positive to negative concavity, or an inflection point. Okay? Now we have to be careful because we cannot assume that second derivative equals 0 is an inflection point, but it's an indication that it could be, and we still have to check for concavity change. So if I take a look at this graph here, we can start picking out points here. Well, A represents the domain boundary, so as I approach A from the positive side, I get the y-coordinate at A. B is going to be that coordinate there. So that is a maximum point. Okay, so what's happening here is that the f prime value at B, I'm going to write B, is equal to 0. We have a horizontal tangent. At B1, it's going to be that point there. Notice that's curving down and switching to curving down to curving up. Well, that's a point of inflection. So at F, we call, well, that's not necessarily F double prime equal to 0, although it can be. So we're just going to call B1 an inflection point. And potentially that could be where the second derivative is equal to 0, but we don't know for sure. C is a minimum, and it's where it's negative. Sorry, it's got 0 slope. So at f prime of C, we know it's equal to 0. And it happens to be a min. This point C1 is an inflection point again. Okay, it changes from concave up to concave down. D represents, again, a max. So f prime at D must be equal to 0. And then the last part here is kind of cut off, but as x goes to E from the negative side, or sorry, from the positive side, it's going to be equal to f of E. So that's going to be our domain boundary, and we can indicate it that way. So we can then start sketching graphs showing inflection points, adding on to what we've done before. So the first thing is we need to find zeros. So we need to factor this. Okay, so I want to factor this. I need to find a factor that works. Okay, so I'm going to use my factor theorem. I'm going to plug in 1. Okay, when x is equal to 1, I don't think it's going to work. I get 1 plus 3 plus 5. Oh, that does work. 1 plus 3 plus 5 minus 9 is equal to 0. So there it is. There's one of my factors. So my f of x can be written in factored form. Okay, one of my factors is x minus 1. Okay, so I just have to break down the rest of that quadratic. I'm going to use synthetic division here. So I'm going to use x minus 1. Okay, I'm going to use a factor. I'm going to subtract. So I'm going to multiply and subtract. Multiply and subtract. Multiply and subtract. We need to end up with a remainder of 0. So I know that my quadratic is x squared plus 4x minus 5. So I'll factor that into x plus 5, x minus 1. Ooh, so we've got a double root at -1. So we can write our zeros at 1, 1, -5. So we have 0 at -5. So it's going to go through that one, and it's going to bounce at this one. Okay, so those are our zeros. Our y-intercept is going to be 5, so I'm just going to make sure that I have a pretty good idea what this looks like now. It's going to probably go through like that, bounce like that. Okay, but we still want to find our max, min. We kind of know that's going to be our min because it's a bounce. Okay, but we're going to find it using calculus, and we're also going to find an inflection point. So let's start with the derivative to find max and min. So f prime of x is equal to 3x squared plus 6x minus 9. That is factorable, I think. X squared plus 2x minus 3. So that factors into x plus 3x minus 1. Okay, so we know that the derivative is equal to 0 at x equals -3 and x equals +1. Let's find our y-coordinate while we're here. Plug -3 into here, I get -27 plus 27, that cancels. +27 plus 5 is +32. Okay, so it looks like it's way up here. When y equals 1, I'm going to plug it in. Well, we know what y equals 1 is. We plug it in, it's going to be y equals 0. Sorry, x equals 1, y equals 0, because we know the minimum bounces here. Okay, so there it is. We have now our max point. Okay, I'm going to -3. It's going to be way up here. Okay, at 32. We also know that that point doubles as a minimum point. Okay, so the last thing is a part now we're adding on that we didn't do before is an inflection point. And I'm going to check for inflection points by finding the second derivative. So my second derivative is 6x plus 6. Okay, we want to find out where it's equal to 0. It's equal to 0 at x equals -1. So that means at -1, okay, there's going to be a point of inflection. Okay, in this case, I'm going to find the y-coordinate because, again, it's fairly easy to plug in. -1 plus 3 is +2, plus 9 is +11, +16. Okay, so at -1, +16, maybe it's going to be somewhere around here. That's going to be my point of inflection. Okay, when I do my chart, I'm just going to shrink this a little bit so you can see my chart. My slope chart, I need to mark -3 and +1. You know, those are my 0 slopes. And I can test my slopes. F prime at, let's say, -4. And I know that's, if I plug it into that equation, I get +48 minus, whatever it's going to be. I know it's going to be positive slope going through there. Okay, so when I plug in the negative value in here, I'm going to get my f prime being positive, so I know it's going up. It's going to have a max here. I kind of know it's going down here, but just make sure we're going to plug in the value. F prime at 0 is equal to -9, so that's negative. We know it's going down. We have zero slope or minimum point. And lastly, we'll test x equals 1, and we know that's going to be positive. Okay, we know that's going to go up in this direction. For our concavity chart, we're going to use -1. Okay, and then just test on both sides of -1. So I'm going to go f double prime of 0. That's an easy coordinate to test. I know I have positive concavity. Okay, and again, our slope graph indicates our positive concavity there. F double prime, let's choose -2. And if I plug -2 into the second derivative equation, yeah, I'm going to get -6. Okay, I know it's negative, which means it's concave down. Okay, so then I know that, and again, notice that the slope chart really confirms what I already knew, or the concavity chart confirms what I already know. So I'm going to sketch in the graph now. I know it goes positive slope through there, max. At that point, it changes from concave down to concave up, and it goes like that. Okay, so there is my polynomial graph.